So welcome to part 3 of lecture 23. So our current story is that we know that we can find a basis so that our matrix MT has this form. So the next thing that we want to do is, can we fill in some of the stars, but maybe at the same time, could we also find the basis that allows us to do this? Okay, and so here's the main idea to find the stars, and maybe here let me kind of correct this, and the basis that we're looking for. Okay, what we're going to use is the fact that we proved in section 8.A and 8.B that this operator, t minus lambda I, when lambda is an eigenvalue, is nilpotent on the generalized eigenspace. So we already saw a strategy to find the basis for a nilpotent operator, okay, so that the matrix was upper triangular. So what we're going to do is basically use the same strategy that we did for finding the operator of a nilpotent operator. Okay, the basis so that the nilpotent operator gives us a matrix that's upper triangular. So what we do is first we find a basis for the null space of t minus lambda I. Then we extend that to a basis of the null space of t minus lambda I squared. Then we keep extending that basis. We make it bigger and bigger and so on until we have a basis for the generalized eigenspace. Okay, and what we want to do this for is we want to do it for each eigenvalue. Okay, so for each eigenvalue. So we'll start with lambda equals 10. Okay, and since the multiplicity of the lambda equals 10, since the multiplicity of lambda is equal to 1, we actually know in this case that the generalized eigenspace is actually equal to the eigenspace. Okay, and why do we know that? Oh, maybe here I'll put 10s in here to make it a little bit more precise. Why do we know this? Well, we know that the left-hand side is dimension 1. We know that the eigenspace is always at least dimension 1, so they have to be the same thing. Since the matrix M of the operator t minus 10I4 looks like, and this we've already done all of this work, is row reduces to this form right here. So we take the matrix raised to the power of 1 here, and we know from here, using kind of some linear algebra, that the null space of this operator is the null space of this matrix, and the null space of this matrix is given by all multiples of 1, 0, 0. Okay, so this is x1 inside of my complex numbers. So this step right here is just basically 1BO3, right? So 1BO3, finding all elements in the null space of this matrix. So what we have is that this is the basis of the null space of this matrix, which is the basis of the eigenspace, which is the basis of the general eigenspace. So we have that a basis for the generalized eigenspace of 10 is the vector 1, 0, 0, 0. Okay, so there's actually not too much to do for this part right here. Okay, the real work comes when we're doing equals to lambda equals 20, because what we need to do is first we need to find the null space of this operator, t minus 20I4, and then we're going to find the basis for t minus 20I squared, and so on. We have to find them, and we're going to combine them all together. So first we start with the basis of the null space of t minus 20 times the identity operator, which is the same thing as the matrix, which is the same thing as the matrix associated to this operator. And I've kind of done the work here for you that you could take this the matrix associated to this operator, row reduce it. It row reduces to this matrix, and the null space of this matrix is all multiples of the vector -1, -1, -1, 1, where x4 is some number in C4, right? And why I'm using x4 is because x4 is the free variable in this case. Okay, so the basis for the null space of this operator is now equal to -1, -1, -1, and 1. Okay, now what we want to do next is extend this basis to the maybe I should put this in here, basis of the null space of this space. Now, how would you go about it? Well, first of all, you would take your matrix corresponding to this operator, t minus 20i squared. So you're taking the operator corresponding to this matrix and you're squaring it, and then I row reduced it. And if you were to use kind of the strategy of Math 1B03, right, you would probably say that the basis is 1, 0, 1, 0, and 0 minus 1, 0, 1 is a basis. Okay, so I'm kind of skipping all the work, right? You're trying to figure out a basis for the null space, right? And that's something you should be quite comfortable with doing. The problem is it isn't exactly the way that we want to do it, because we want to take this thing and then extend it to a basis for this bigger space, okay? So instead, we want our basis to be given by this, right? So we have -1, -1, -1, 1, and then we have 1, 0, 1, 0, right? So this is the basis of the null space of t minus 20i, and then the two of them together are the basis of the null space of t minus 20i squared. Okay, so we're kind of extending our basis, we're adding a new element to it, and then we keep doing the same trick. We extend this to a basis of the last null space. So this matrix here row reduces to this matrix. We already have two basis elements of the null space, so we need one more. There's one more vector that we can add to it. So we already have two basis elements, and then the vector that we're kind of missing is 0.3 minus 1, 0, 0 is also in the null space, okay, and not in the span of the other two. Okay, so it's not in the span of the other two. So what we have then is that the null space of this the null space of this operator, which is equal to the generalized eigenspace, is going to be the span of the following three vectors. Okay, and that's, we only have to find a basis of three elements because we proved that the generalized eigenspace has dimension 3. So we just needed to find a basis of three linearly independent elements. Okay, and so let me write that down. So it's our desired basis since the multiplicity is 3. So we had to find a basis of 3 things. So we're going to pause here, and then in the next part here, we're going to try putting all these pieces together to kind of finish up the proof, finish up the example.